Thanks everyone for coming. We're here for our December webinar, and today we're going to talk about hydronics, pumps, and ways to save energy. And I have with me Danilo. Why don't you move the next slide, Danilo? And I was going to have Bob Vorwald, but we have some technical problems. I thought Bob would be a good co-host, and he might show up. We'll see. But in event he doesn't, there's still me and Danilo. Danilo is going to. He will.
Hey, John, can you hear me now? Or?
Oh, he is here. All right. So Robert Vorwald, or Bob Vorwald, is here. He's going to be my co-host. He's my co-host because occasionally I end up giving these webinars in parking lots or in foreign countries, and I think it'd be better off if we just had someone who could just do it from the United States. So that's why he's here. Okay, Danilo. He's going to introduce himself and his topic, but basically he works for Grundfos. They're a well-known pump manufacturer, and I think that's all I can tell you. Why don't you take it away, Danilo?
Sounds good. Thank you very much, John. Yeah, hi everyone. My name is Danilo. I am located right now in Northern California, United States. I have been working for Grundfos Pumps for 4.5 years now. Spoiler alert, I am actually an electrical engineer, not a mechanical engineer, so it's quite interesting how we ended up here today making this conversation about hydronic systems. And so I started my career back in Brazil, where I grew up. I worked as an electrical engineer for a local power grid company, moved to Denmark, started working with telecom and softwares, and that's when I joined Grundfos Companies, which is a Danish company. Worked there for 1.5 years, where I would be making presentations and receiving the American customers to our product center at the time when I got the invitation to say, would you like to have ever considered moving to United States? And I was like, not really, but why not? And here I am. So been with the company for 4.5 years, been in the United States for 3 years now. And I'm happy about it. So thank you very much. Are we having Rob's making an introduction as well, Jen?
Yeah, Bob, why don't you give a couple-minute introduction?
Okay, assuming you can hear me okay now.
Yes.
I'm currently, I finally retired from full-time M&V work and such. I think John and I know each other back from, I don't know, late 80s or something. So I've been in the energy services game quite a few years, and worked for a number of ESCOs during that time frame. Johnson, Siemens, Train, kind of the usual characters. And also I've worked as a customer, as an energy manager for a local school district here. I live in Utah, and I spent about 20-30 years flying everywhere else to do work. So and I'm currently teaching at local community college, staying in the energy game, teaching energy management, building automation systems there. So.
All right, perfect. Thank you.
Great.
All right, Danilo, take it away.
All right, so minimize energy usage and maximize efficiency. So my job today at Grundfos is basically focused on what we call sustainable replacements, right? Supporting and helping end users on how to identify the highest efficiency possible solution for their mechanical room and hydronic applications, plumbing applications as well. So today what I prepare for we to talk about is, why should we discuss it at all, right? Why are we talking about energy optimization, and how do we identify the energy savings? And so the identify energy savings is very focused on the pump equipment itself, not as a pump system as a whole. And then I want to go a bit broader at the end, and then we're going to discuss about distributed pumping and looking at a complete hydronic system and how do we also identify savings in there, right? If you have any questions, I guess, John, are they coming to the
they'll write
and
them
then we
in.
answer them at the end?
Yeah, they'll write them in the questions box, and then I will, me and Robert will read them off in the end.
Sounds good. Thank you very much. All right, so let's get started. So why energy optimization is important. If we look only at pumps, for example, right? If today everyone switched to their pumps, to high efficiency pumps, we could actually save 4% of world's total electricity consumption. How much is that? Well, that's equivalent to the residential electricity consumption of 1 billion people. You couldn't reduce the whole energy consumption of a country like India and China, but besides those two, you could save a lot of energy for domestic houses. And another trends about what are we doing here, legislation, volatility, and market trends. So that's why we're also focused on energy optimization today. On your top, when you see legislation, right, you have current trends, different markets. I understand we have participants and attendees here on this webinar from different locations, right? So different cities, states, countries, they're gonna push more towards their legislation and make more energy efficiency as a necessity, right? On top of that, we have volatility, energy prices keeps increasing in some locations. Here in California, as prices kept going up and up, Fastly, I was very surprised, John, that a few months ago, I actually got an email from the local provider, PG&E, mentioning that my bill went down about 3%, which was surprising for me. But anyway, volatility. On top of that, since we're focused in commercial buildings, right, since COVID-19 pandemic, it really changed about how we utilize commercial spaces, right? How do we utilize the buildings? So that's also very interesting. And then on top of that, this market trends, how these things evolve and keep changing, right? It just drives more for circular economy, right? Which is becoming a new market standard. And the idea is just, continuing, let's say from the manufacturer side, how do we continue production in a more sustainable way? But also like from the end user side, right? How do we keep things more sustainable and environmentally friendly, right? On top of that, next, we have the demands, right? So again, why do we focus on energy optimization? The demands for commercial buildings, they keep on rising, right? The construction of buildings generate 38% of global greenhouse gas emissions today. So here's a few global data for you guys. Global use of energy is projected to increase almost 25% by 2050. And most interesting here for the aftermarket for identifying, walking in existing mechanical rooms today and identifying opportunities for energy savings. 80% of the installed base are between 20 to 30% oversized. So most of the equipment today, they are in some cases grossly oversized or at least oversized equipment installed, right? Now, if we look into that, talking about commercial buildings, there are different types of buildings, right? Different types of applications, and because of that, they have different types of usage, which will require different consumptions. So we're talking today data centers, district energy. I think this is very popular, at least in my region today, for big higher education, universities. We have mixed use, high-rise residential, transportation, healthcare, hospitality. We have industrial plants as well. We have big offices, sports and leisure. We have World Cup happening next year. We have the Olympics, Winter Olympics, government, education, and also retail spaces. Now, just focusing on HVAC and hydronic applications, when you look to your right side and look at the top, starting from hospitality, hotels, you can see that HVAC energy consumption is equivalent to about 25% of the total electrical energy consumption. While for healthcare, right, a building such as a hospital, the HVAC system generally represents 52% of the total energy consumption. Are we already like here in more than the half of the total energy consumed solely by the HVAC system in this kind of buildings. And as I mentioned, district energy and education centers, the HVAC system generally represents a whopping 66% of the total energy consumption. Because of that, that's why we're focusing and we're having this discussion today based on these hydronic systems. Now, when we talk about pump energy consumption and we talk about how do we optimize energy, this is very important because when we talk about the pump life cycle cost, right, the LCC for the pumps, the energy expenses represent the biggest cost during the whole pump life cycle, right? So it's very common when you are in a building today, you're a stationary building engineer, or you're a contractor that got hired by the building, and you got to replace an existing equipment, and you got to do it quick, right? So I don't know, due to ethic reasons, you're gonna look for the 3 bits, you're gonna find all the 3 ones that work, you're gonna get the cheapest one, and you go for it. But I mean, have you done any previous study about who selected those and what it's contained into that quotation, right? What's the selection of that pump system? So today, pump purchase, if you consider the whole life cycle cost, is only about 5%. We can actually break this down into more, right? Especially when we talk about lifetime maintenance costs, how much you spend on maintenance, this number can vary a little bit, right? You can have, again, depending on how the pumps were sized for that application, how they're utilized, how they're maintained, the maintenance costs can start going higher and lower, and that already will tell us what's happening with the pump. But then again, the main focus of our conversation today is lifetime energy expenses, right? It represents about, I want to say, 80% of the pump. And again, that's all based on an average, because depending on the location and the cost for electricity, those pumps could actually, the energy expenses could represent a bigger number than that, right? And so what's next, right? What happens if we don't optimize now? Leslie, on average, 30 to 40% of the energy in commercial buildings is consumed by HVAC systems, as we saw. But if we don't optimize today, what happens is you start driving OPEX, which means you start having much more costs for operation and maintenance with those equipment, which can end up lowering not only the property value, the property standards, right? If you have any kind of LEED certifications, and also compromising the comfort of the guests of that commercial buildings. So moving on, this is to complete with why energy optimization is important. Now, next is how do we identify energy savings? So let's start with efficiency, right? So let's start with pump curves. Once again, we're looking at pump curves. How we don't talk about pumps without looking at pump curves. I'll start by the right side. You see 3 curves. You see the dark blue one, it's the pump curve. You see the green one, which is the efficiency curve, and the light blue one, which is the reliability curve. We'll go one by one. We'll start with the pump curve. Once you want to make your selection, right, at the bottom you have the flow and head, which pressure you need to overcome. So once you find that point, you're going to identify the pump curve, what is the duty condition of your pump. Now, one thing you got to keep in mind is that you always got to look, when you're sizing a pump, selecting a pump, you got to look at the best efficiency point, the BEP, right? You got to look at the efficiency curve. Rule of thumb, when a lot of people, and I understand, I've been in that place before, if you don't have much knowledge yet about the pumps and you're going to look at a pump selection, once you find your point, where is your duty condition, you just want to be right in the middle of the curve, correct? Wrong, right? If you don't analyze the efficiency curve, you cannot tell, right? As of today, you see this curve here, it looks pretty much in the middle, but what happens is manufacturers, what they can do is, Well, if your selection is right here, right at the right hand on the end, what I can do is I can extend that line, and all of a sudden your selection looks at the middle. So always make sure you're at the highest efficiency possible for that duty condition, right? Now, what happens today is we're going to talk about if you're running your pump outside of that region. And that is because in a few slides, we're going to talk about part load conditions, right? The demand in a commercial building, it's usually not constant, right? It's not always the same, and that's going to vary. Once you're varying that, you start increasing and reducing your flow, you start getting into trouble if you're going too far out of your best efficiency point. As you see a few examples here, right? If you start running too much to the right side, that's when you start having lower bearing and seal life. Also to the end side, you can also, on the left side, you can also have low bearing and seal life. If you go too far out, that's when you start getting cavitations, right? And at the beginning, you can also start running at a lower flows. You can start not only having cavitation, but you can start also having like recirculation, discharge, and the suction side of your pump, right? So quoting here, Hydraulic Institute, in 2017, they came with the pump guidelines for what is allowable and preferred operating ranges, right? So if you find your selection here, how much far out on the right you want to go, how much far out on the left you're allowed to go, right? So the preferred, you always want to be on the preferred, the POR, preferred operating range. You want to be from 70% to 110% of your best efficiency point, right? And allowable, you can go all the way from 60 to 120. Is that okay? Well, yes. Are you going to be able to deliver water? Yes, but you don't want to spend too much time outside of the zone because as you can see, you can start getting into trouble, and reliability together with efficiency, they go hand in hand, right? Another thing I want to mention is, I want to bring another slide here so you can see. Okay, a similar curve here. If we only look at the pump curve. So here I have a little picture of what you can see on the preferred operating range, compare also to the allowable operating range, right? But if you look at the downside curve, now we see a vibration curve. So you see that when you are here, this is the BEP, right? Your best efficiency point for this example, that's when you have your lowest vibration. And you see how once you're out of the preferred operating range, how quickly the vibration starts increasing, right? And you don't want that because the more vibration you have, the more energy consumption you're gonna have. So that's about efficiency. Now let's talk about efficiency, as I mentioned, on part load conditions, right? What is the typical building load profile? So when we're looking at a building, at the bottom here, you can see in a percentage, right, of the load and the demand. Are the pumps running at 25%, 50%, 75, or 100% of the load? And then here you can also see the operating hours on the axis here. Now, what is interesting is that you're going to see that most of the time the pumps will be running at 50 to 75% capacity, right? You would rarely see a building case where they're going to spend time on 100% load. What does that tell us, right? It says that this explains a lot. Why are we still seeing equipment today? If you walk into a mechanical room, why are those equipment oversized? Because many engineers were still sizing pumps for the 100% load. So what happens here is, if I go back a few slides, right, when we look at this, we're selecting the best efficiency point for the 100% load. Do we spend any time in there? Well, we spend only about 1% of the time, 3%, maybe 10% of the time, if we ever get to 100% load, right? And then after identifying that, engineer, you always also gonna add that safety factor and it's gonna upsize them a little bit more. what happens is now you run your pumps too far out of the curve at part load conditions, which means most of the time you're gonna be outside of your preferred and even maybe the allowable operating range, right? I have an example. Bob's gonna like this one because this is from Salt Lake City. This is a building we take an analysis on the data. So we have three pumps. It's a three-pump system. And then you have a capacity for them was 6,750 gallons per minute. What we measure after looking at all the data from their BMS system, the max flow measure was 4,368, right? This we're looking at from 2022 all the way to the end, to summer 2024. So we have about 2.5 years of data here, while it never reached the 6,000 gallons, right? This is the max flow register. And the existing nominal, the pump nominal head, right? It had about 166 feet on its nameplate. But if we look at the graphic, it will show that the typical head was actually from, instead of 166, it was only 35 to 45 feet. Also noting that the average speed of the pump, so these pumps, they are on VFDs, right? You're noting that the average speed is 42%, and I have some more data where we can see their load profile. So here we have 6 different types of duty conditions, right? We're going from 1 to 125 gallons, 125 to 50, and so on, all the way above 1,000. That's the average. How much time do we spend in each range here? So as you can see, most of the time we're spending within the ranges of, I want to say 125 to 500 gallons. How many pumps are running at that time? You have one pump only. So what happens in this case is that you see right there the waste of energy, right? You're having now reducing the speed of those big motors to only run at this certain speed here. You see their operation, so at least one thing we know, the control installed made sure to have all the pumps running the same amount of hours, so that's well split. However, you can see pump 1 operates only at this kind of speed, an average of 18%. 40, this is not the hertz, right? We're just talking about percentage. So average speed is 18%, 41, and 41%. So I'm assuming here we have pump 1 running as some sort of a pilot pump, jockey pump. And then when needed, bigger loads, you have pump 2 and pump 3. So here shows huge opportunity, right? Once we analyze the data, we can now correct size this equipment. Besides, now we spoke about efficiency, right? How to select the pump. And now we're talking about load profile. So next, I want to talk to you guys about the hydraulics, right? How do you identify hydraulics? How do we find savings? Hydraulics is another very big, important part of it. Pumps are designed, I want to say, at least the Grundfos pumps are designed to run for 25 years, and it will depend very much about how they operate, how they're maintained. But we know our customers, they expect to run them for much longer than that. I personally have the experience of walking into buildings and seeing pumps from the 80s, from the 90s, and they're still running, right? So here, at least in United States, what happened was in 2016, that's when the US Department of Energy, the DOE, started issuing the first ever energy conservation standard for certain clean water pumps, right? And then working together with Hydronic Institute by 2020, that's when the DOE reviewed the process and then they updated regulations. From that point on, all manufacturers in the United States, they had to change a certain hydraulic parts to increase the efficiency of their pumps, else they wouldn't be legally allowed in the market. And that's when it came what we call here the PEI, right? The Pump Energy Index, Efficiency Index. And then what you can tell is this is very recent, right? We're in 2025 and we're only talking about 2020. So not just by that, you can tell that many pumps that was manufactured prior to 2020, they already have uh, low hydraulic efficiency, right? So the hydraulics, by just replacing an older pump for a newer pump, you can already find, I want to say, about 5% on energy savings here. Besides the hydraulics, right, all pumps, again, we're talking mostly centrifugal pumps, right, rotating equipment. Besides the hydraulics, that's when we come with motors, right? That's another good part for it. Interesting enough, actually, yesterday I was participating in a training. I was doing an 8-hour course with the Hydraulic Institute about looking at the whole systems and how do we identify. And we did a couple exercises about how do we find savings. And one of the exercise was just replacing an existing motor, which was a premium efficiency to a super premium efficiency. So we gained about 2% efficiency on this motor. And our energy savings at the end, once we calculated, it was 0, right? So we just went from one motor to another, running the pump at full speed. What happened is you increase the efficiency of that motor, and that generated a little bit more head, and now you got more pressure. You have more total power consumption in the system. So one thing, and then like you win on efficiency, but then you also deliver more kilowatts, and that kind of like they even out at the end, and we calculated no energy savings, no gains in there. What we are introducing here to the market is ECM, permanent magnet motors. That's the best way here, which in the United States, that's how we call, like in Europe, we have the IE standards, right? So it would be considered an IE5. Here, it's not, I guess, standardized yet. Yet it's not a thing, certification in the United States, but you'll be classified as some ultra premium efficiency. So as you can see on this graphic, right, how efficiency goes up compared to the power outside power, output power. You see the difference of it. So the top line, that's when you have the highest efficiency, permanent magnet motors, whenever possible to utilize this. That's your highest efficiency. You can also notice that the output power will go together. It will have a very similar curve here when you're running them at different speeds. So when you start going at lower speeds, the curve will look very much the same. The difference is that this curve is going to drop down a bit faster, right? So when you have premium efficiency, high efficiency motor, and you start running them below 800, you're around 600 RPMs, your efficiency is going to go down really, really fast. While the i5 motors, they are still somewhat a bit more on the flat side and keeping their high efficiency. Another interesting thing is about how these motors are constructed. Is that the super premium efficiency motors, they usually gonna have the little fan. Not that this one doesn't, it does, but just because of how they operate, the turn down ratio for a regular motor, it's about 25 to 30%. So you cannot run them lower than that. You also probably don't want to because of their efficiency, but also that little fan which runs together with the shaft is not gonna have the same cooling capabilities, and now you're having overheating of your motor, right? So this kind of motor, because of how they operate, being permanent magnet, you can go down all the way down to 7%. We actually have a circulator pump that we can bring it down all the way to 7% due to how we keep it cooled. On top of that, what I want to show here, just a comparison. You can save from about, by just utilizing an i5 motor, you can save about 7 to 10% on energy cost, even compared with this motor. And again, I'm not just comparing like this motor, they automatically is gonna have a VFD, but we're also comparing this other super premium motor with a VFD, right? So just by utilizing these motors with the VFD compared to this to the permanent magnet motor, you already have 7 to 10% on energy savings. So we've been on hydraulics, motors. The next thing is, I want to say, how to identify savings is how do you control your pumps, right? Controlling the pumps, it's again, very important because now you got to identify how far are you from the best efficiency point, right? If we're looking to getting more modern systems with drives and so on, you have the capability to now control the pump and run where you want to. What I see mostly in the market is, let's say, a 2-3 pump system. You run the first pump as some sort of a soft start. You run that pump up to, I want to say 90%. And once you reach the 90%, the second pump kicks in. Now, what happens is you base your curves on just speed, right? You could take that pump out on that controller. That controller is only checking, getting a signal of speed, frequency, and feedback and going back. You could take that pump out of that loop. You could put a fan on that loop, and the controller will do the same thing, right? What you want to do is you want to be able to track efficiency points, right? And run that pump based on efficiency. That's how you want to optimize your pump sequencing, right? And all of that is, what is it better, right? In that case, are we running on constant curve? Are we running on constant pressure, right? Now you have newer systems can allow you to keep the pressure and just based on variable flow. Now that could also, depending on your system, as your pump flow goes down and you keep in that pressure, the efficiency goes down as well, right? So these curves are always like looking at efficiency. So you got to maximize what's the highest efficiency for your application. And then lastly, this would be another thing we talk about. It's a bit more, I apologize for being kind of product heavy, but what we're trying here is, as you're going to see, you have all newer hydraulics, ECM motors, but the idea is modular systems, right? What we're talking about is increasing modularity. That's another way of having the same. I actually want to say that this is not how you identify, this is how you solve those problems, right? When we're talking about part load conditions, you want to have at least, let's say, one pump size for that 50% load, and then you maybe be able to achieve the 100% load with all the pumps, and then you can add a redundancy if you want to or not. And nowadays with technology and improvement in manufacturing, as you can see in the pictures and example, you can increase number of pumps and actually save on footprint because of package solutions, right? So it's very simple nowadays to save on space and increase in modularity and increase energy efficiency. Okay, now I'll move to the last part. So this is when we talk about all the pumps and looking into pumps applications only, right? So we spoke about part load, hydraulics, motor, controls. We also, now I want to talk to you about looking a bit broader into the system type. So we want to talk about, for HVAC applications, distributed pumping, where the idea is to reduce the pressure, improve performance in chill water systems. Actually, we can also do this for heating hot water systems, and so mostly like comfort pumps, and also for hot water recirculation, open loop systems as well. Now, this is a more holistic approach, and I cannot talk about it without talking one of the Grundfos pumps, which is our circulator. And the reason I'm talking about this pump is because of this sensor that the pump would have, right? So now the pump already comes. This is what we're gonna call like, so you have an ECM motor, a smart pump with a differential pressure, or it can also be utilized as differential temperature sensor already standard with the pump. Is just an example, so you have an idea about size, how it looks like. So we're talking about circulator pumps. This is a hospital in Southern California. So why am I talking about this pump is because here's what we're gonna do. So here you have your common variable primary chill water system, right? And I wanna look at a first couple of pain points about what is the challenges today in this kind of system. Again, number one is your delta T, right? How do you control delta T? and you have ASHRAE standards. What is an ideal delta T, right? When you're specifying that building. Number two is how do you keep comfort, right? Are you compromising on comfort for your guests? Today, when we look about many solution providers, right? If we're talking ESCOs here, and we talk about that ESCOs working with different companies. My partner works in the industry as well, and it's actually quite rare to identify solutions today that will increase, how can I say, you will decrease energy, right? You will save on energy without compromising on comfort of your guests. So luckily, this is something that we can deliver here. Another thing is time consuming for balancing and commissioning process, right? How are you going to balance all those valves, which that is what's going to deliver the comfort to your guests, right? Or if some people are struggling with temperature control. On top of that, you could have complexity in design, installation, commissioning. I'd say 3 and 4 to go hand in hand. And lowest, low efficiency pump, that's the last one, not least, but low efficiency pump management for your primary pump. That's exactly what we spoke in the past, right? So let's say the few slides I just presented, we'll be only looking at this pump application, you know. Does he have the improved hydraulics? Does he have the high efficiency motor? Are you controlling it to the high standards? And are you also, how did you size that pump, right? That's how we look here. But now if we look at everything, how do we increase that? So the idea of distributed pumping is that we want to eliminate those valves and those throttling valves, because basically what those valves are delivering to you is just more pressure for your pumps, right? All your pump has to do is overcome the pressure, the head generated by those valves. So the metaphor we usually like to mention in this case is kind of like your pump is the gas and your valves are the brake, right? And what's happened is you have one foot in the brake and you're just one other foot on the gas. You're pumping while you're braking at the same time. And the idea is removing that, utilizing those pumps, and that could be in the inlet or the outlet of your air handler system, right? So with that, again, important, you need a decoupler. And here's where we're tracking temperature. We utilize temperature sensors here and start measuring the temperature. So what happens is you reduce all those valves. This pump will run based on differential temperature. It will know the temperature. This is not like one pump needs to communicate with each other. No, they just do that by itself, by the little sensor I showed you. Okay, so now you're reducing that. Why do we do that? Now you have free flow in your system, right? They're self-balancing. Now what happens is you can reduce that head significantly. Now you're gonna go from a much bigger pump system here to a much smaller, because now all you really need, your pump really needs to do is basically deliver, as people say in the industry, keep that chiller happy, right? You're just delivering minimum flow here for that chiller. So this is what we will call the distributed pumping system in essence, right? So again, as I mentioned, we want to reduce valve authority. Here in the United States, ASHRAE recommends the valve authority to be from 50 to 70%. You want to reduce that. When the more valve authority, the less valve authority you have, the more energy savings you have, right? The more valve authority, the more energy consumption, the more head you're creating in your system. And then your system, needs to overcome that friction loss. So, not sure if that went too quick or not. Try to be short and sweet. I guess
that was good.
Go for questions.
That was good. And I want to ask a few questions, and I've got a few from the listeners as well. I'll bring my picture back up. Hey, Bob, you can bring your picture up if you want to. Okay, so my first question, I was doing an energy audit recently and looking at, maybe we should replace the existing motors. I don't remember if they're standard or premium. I don't remember, but with EC motors. And the EC motors thing seems like it's not so simple. It's not just like replacing a standard efficiency with a premium efficiency. That seems easy.
Right.
But the EC, it's like, wait. They sometimes or always have built-in variable frequency drives. Maybe they don't call it that, but a speed control of some sort. and
Correct.
you just don't replace like for like somehow. I don't understand that, but why is it so
Yeah.
hard? And it's just not a
Yeah.
simple thing.
I would agree with you. I think because I don't want to say it's new in the industry because it isn't really, it's been here for like a decade, I want to say. The thing is the built-in, they require, right, built-in drives or some speed control system. And I think also because of their size, you're going to have different manufacturers. So I work for Grundfos and we manufacture ourselves. I have also known that our limitation today for ECM motors is 30 horsepower, right? And then we only have a few certain frame sizes that will match with the specific types of pumps, which there's
Right.
also another thing you got to keep in mind because each pump, they're going to have their different frame sizes. And as working with a customer, we identified motors that actually they wanted to utilize. Let's say the customer wanted some 40 horsepower ECM, and then we cannot deliver that. So then I start reaching out to Baldur, ABB, WEG motors, and I learned that everyone is kind of kept at 30 horsepower. No one is delivering ECM motors above 30 horsepower. And then I also started learning that the more you increase the horsepower of your motor, they are already like, because of the winding, right? The smaller they are, much more sense it makes. But when you reach a certain horsepower, you have so much more like winding that it's already like the efficiency gains are not that much. But I think that's what I want to say yet to you is it's the limited, I want to say, not only acceptance in the market that not everybody's going for it, and then now that they decide to go for it, manufacturing is not keeping up. So I think there is more this evolution of how much is utilized today,
Yeah, it's just theoretically it sounds great, and in practice it's not. So like for example with pumps, you want to what we would do is just take the motor out, leave the pump there. But now it seems you have to take the pump out also and the motor out and then put in this new whole system. So it's a lot more complicated and more expensive than we want it to be, I guess.
Yeah. I mean, I want to be neutral here, right? But I think the idea is, I think we could have more regulation towards having a more universal, as I said, frames fit for the motor to be utilized in different types of pumps, right? As of today, whoever manufactures, you're gonna do for your pump only, right? So I cannot just take the motor, existing motor, and put a Grundfos permanent magnet motor on that pump. I got to take the whole thing, and then I'll come with a Grundfos pump with the motor, right?
Yeah, that's what I thought.
That's not ideal.
Here's another one. So people who do energy audits, a lot of us, not all of us, but a lot of us, we look at the fan laws, right? Or you've seen that where, you have a VFD on a motor and you drop it, you drop it to 85% and you're only using 50% of the power. Theoretically, it's not really 50, it might be 60. And, and if you drop it to 50, then you're using maybe 15%, or I don't remember what the number is, but something like that.
Right.
But what you're saying, from what I saw, you were saying, yes, if you drop it to 50%, you're only running your pump motor at 50%. Now all of a sudden your pump is way out of range. Then all of a sudden the pump is super inefficient, so that our representation, what we thought was saving, 85% of the energy, it's not. It's saving a lot less of the energy. Is that what you're saying?
Not necessarily, no. So I did not have a graphic here ready for this presentation, but if we're looking at a pump curve, right? Let's just imagine the pump curve, and as you're running them on a VFD, you're now reducing the speed. If you're familiar with the pump curves, it will be pretty much, not the exact, but very, very similar to the impeller trim, right? So you can reduce the speed. That just means that curves start going down, right? And the efficiency curve is going to be kind of matching. So it depends a lot of your system. You got to take your system pressure into consideration, right? The head of the system. So if we're talking hydronic, friction loss in hydronic, like closed loop system, they're much lower than a plumbing pressure boosting efficiency, right? So when you reduce your, I want to say, if you reduce your speed, you can also ask for your pump manufacturer for that kind of curve. When you reduce your speed, you can have your efficiency curve based on different speeds, right? And just all you want to see is how far can I reduce the speed until I keep within the preferred operating range? Does it make sense? Let's say
Yeah.
if you go down all the way to 55%, you're still between preferred operating range, but you go down to like 40 or below 50 for that specific application and pump, now you're out of it. So you got to take into consideration the curve at different speeds, and then you can make your decision based on that.
Okay, let me see. I think I had one more question, and that was, so you showed us the first pump curve you showed us, you were talking about, whether or not, is this pump oversized or not? And you, and I thought, that what you were saying works for designers, but not energy auditors itself. And my question
Yes.
was, and maybe you kind of went over this later, is how would someone who walks into a building determine that pump's too big? It's too darn big.
Well, assuming that every commercial building is going to have a variable demand, it's very easy. If you walk into a building and you say, let's say, a big pump, our rule of thumb when you're looking at energy optimization and the low hanging fruits, it will be a 50 horsepower and above, right?
Mhm.
That's a rule of thumb. And when you see a 2-pump system, which is full duty standby, that's
Okay.
waste of energy right there, right? Because that pump is already sized for the 100% load, and you're not varying anything. So I'd say that's already like an easy beginning when you walk into a mechanical room and you see only a 2-pump system sized for duty standby. Especially if it doesn't have any drives yet, still, you're not even modulating.
So you
I
would
guess that's
replace,
a
like,
good rule of thumb.
if you had 250 horsepower motors and pumps, you would replace that with, and one is standby, you would replace that with 225s, you're saying, and run them both at full load.
That's a very interesting question. That's a very interesting question. So yes, when we are making selections, we're looking at the whole life cycle cost, and I've had different experiences with this. So yes, if I have, let's say, 250 horsepower, ideally, let's say if you could increase modularity, you will go with 4 pumps, 25 horsepower, right? But again, based on energy and the hydraulics efficiency, because those pumps are now from the 90s, right? And the 80s. So what happens is you don't need that much horsepower to deliver the same thing nowadays. So very often what I come across when we're finding energy audit applications is that you can actually deliver that with a smaller amount of horsepower. And I want to say that's not really an audit, because inside of Grundfos here, our terminology for audit, when we do the pump audit, that means we come with equipment, start tracking, like I share a field of data from their BMS, right? You want to start tracking all their flow consumption, their differential pressure consumption, their power consumption of their motors, and then we size an equipment based on that. And that we reduce horsepower drastically when we do that.
Okay, Robert, do you have any questions?
Kind of on similar terms. So I think early on you had one, you're with the pump curves you're showing, traditionally pump was picked based off highest efficiency and design load. And we're saying, okay, chances are design load again, 5% of the time. So if we're retrofitting, again, we're doing an audit, we're making a recommendation. If we have trend data, that's an assumption of some type with flow, and we realize 60% of design is where we're spending 80% of our time. Should we then repick, if we're replacing, pick that new pump at that peak efficiency at that reduced output level, I guess, of the pump? But are we ever in danger then of not being able to hit our peak again on that 1% day or 5% day or something?
Very good question. Yes, no, so you're spot on. You want to select your equipment based on the highest consumption, right, demand. That's when you want to have your highest efficiency. But again, what we are also talking about is increasing modularity. So you're not sizing one pump that is going to have only the highest efficiency there, but then now you're not going to get to the 100% anymore. You want to be able that you achieve those peak demands. The difference is now you're getting out of the range there, right? Because you only expect to spend 1% of the time there. And actually,
Okay.
as you saw the Salt Lake City example, you don't even get to that peak, right? You never.
Right.
That pump was
Yeah.
selected for 6,000 gallons at best efficiency, and it never reached that, right?
Sure. Okay. No, I like the idea of going to the modular side of it anyway.
Okay.
Coupled with that same kind of question, or down that same road, is if systems traditionally, and we've all seen it where they seem to be designed way bigger than they needed to be. Does that also, from your experience, translate from what you've seen the rest of the piping system? So not just the pump now, we're talking about the thousands of feet of pipe in this building.
Yeah.
Let's say maybe primarily the primary loops and major
Yeah.
secondary loops. Are
Yeah.
And does that create a problem with our or concerns or things we need to look for in selecting the correct
It's a great question.
replacement pump?
That's a very good question. That's a very good question, and it's actually really hard to measure that, right? To get data on that. As being a Grundfos person, I'm only talking about pumps. But again, like as I was in the Hydraulic Institute course yesterday, we started looking outside of pumps. And one way of reducing, increasing energy savings, right, reduce energy consumption, is also increasing the size of pipes, right? You could increase the size of your pipes, and now you're reducing the pressure loss. So now you can the demand on your pump is lower, or you can also downsize your pump. So definitely, I would say that over time, your area inside of that pipe is smaller. So now you probably have some much more like friction loss, right? You have more pressure that you need to overcome. However, again, we cannot calculate on that. And a good example for that is that when we're doing an energy audit, we always want to get flow meters and get how much water is going through that pipe. And it's very challenging in old systems to get any flow data because those pipes, they get built up with so much stuff inside of it that you cannot see what's in there. And that's already an example to answer to your question, right? So definitely something that could be a concern and really difficult to address.
Like I said, it's one of those unintended consequences we got to be careful of sometimes. I don't want to, fix one thing and create another problem that was unforeseen. Let's
I
say.
know with steam, that's certainly a problem. That is certainly a problem with steam. If you lower the pressure, then you need bigger pipes. And it's like,
but I would like to add a comment that, again, I'd say that you're still tracking the data, right? Regardless of what is the dimension of that pipe and how much is inside of the pipe, your pressure, differential pressure, what your pump is pumping, right? And how much flow you're tracking, that's still the same. And you're gonna size the pump based on that data. So it's very important that you collect data and you make less assumptions and more data-based decisions.
Okay, I want to answer some questions from the listeners. One was, what sizes do the EI5 type motor come in?
Yeah, as we spoke before, John, I've seen today in the market up to 30 horsepower.
Up to 30. Okay.
Yeah.
Good. Let's see. I got one. What piping and pumping design do you recommend for VA reheat designs while trying to minimize control and balance valve quantities? I think he's talking about distributed pumping, right? I mean, that's how you minimize valves and
the valve authority
problems, right? It's a distributed pumping system, but the question is, what piping and pumping design do you recommend for these distributed pumping? And I don't know the answer to that because I don't know the
I mean, it's really hard to come with an answer without knowing how the gallons per minute, the flow, the pressure you're overcoming, how many feet of head, right? But I mean, yeah, your pipe size is gonna change based on that, and your pump as well is going to change based on that. So it's I mean, we can definitely support if needed. You can share more information and more data. We can
Okay.
take that out of the call and help.
Okay, yeah. So Grundfos actually they actually help people doing energy audits and stuff. I mean, they're not going to do the audit for you. They're not going to show up on site, but I've called them up and they've answered questions for me. Here's another one. Could you talk a little more about selecting pumps relative to peak demand, especially for multiple staged pumps?
Well, it's an interesting question, and if it's a multi-stage pump or not, it's going to be the same, right? You want to look at a curve, and a multi-stage pump is going to have, it's a pump that delivers, let's say, it's a low flow, high head pump. So you overcome a lot of pressure. It's a big like pressure boosting pump. And what happens is that that curve is going to look slightly different, right? That curve, it's going to be more verticalized kind of type, but still it's not going to change. You just want to see that curve, see what is that you're looking for, right? How many gallons per minute at what head, and you want to look at, again, compare that point with the best efficiency. That's how you're going to find the pump. So you're going to have a selection of different pumps. You see which one has the highest efficiency for the load condition, and there you go.
Okay, here's one. Are you able to describe similarities or differences between a distributed pumping solution you described and using the Belimo energy valve or similar products? I think that's what it's called. I've heard of that product, but haven't gotten familiar with it.
Yeah, so energy valves, the idea, you're using throttle valves, right? So you have, again, you're still having valve authority in your system. What happens with the energy valves is that they are more efficient than the mechanical valves. So you save energy by going from a mechanical valve to an energy valve, definitely, but you're still creating that pressure for the primary pumps, right? So if you look at your secondary loop, you're saving energy on your secondary loop, right? If we look at just the first half of my presentation, the beginning, when I talk only about pumps, pump system, controls, motor, we're only looking at the first loop, right? The primary loop. That's how we save energy on the primary loop. And then I want to say that if you want to save energy on the secondary loop only, then you look at only energy valves. But then if you want to look at a system as a whole, that's when you want to reduce valve authority and then just let the system flow, right? Because that would also not only reduce all the valves, right? So that you're going to have flow more efficient as far as not energy, but more like comfort on your secondary loop. And then because of that, you reduce your primary pump size, and now you have energy savings there.
Okay, so here's another one. This one is, so the proper way to retrofit a pump system is to look at the trend logs of the existing pumps and then size the new pumps based on the highest percent of time the pumps have spent at a specific load. Well, I think that's only half the story.
Yeah.
Can you address that?
That's correct. Yes, that's exactly that we're trying to achieve today, right? The challenge is, and I think as you guys like ESCO companies, the challenge is how do you find that load, right? How do you know what that pump is doing, right? And that's what you go over in audit, right? How do you get that information? Because not everything is on BMS. Not every BMS is storing the data, right? You don't have the data storage. So you're spot on what you want to achieve and deliver. The challenge, I'd say, is actually how do you get all the information to get to that point?
Okay, so Danilo, so in this case, let's say they had 100, let's just say 100 horsepower would be the correct size pump for the maximum load, but they're only there 2% of the year. And most of the year, they're only at, let's say, what a 50 horsepower pump would deliver. So the solution would be just to have 2 50 horsepower pumps, right? And then so you can just run one 50 horsepower most of the time, and then when you really need to, you can turn on the other one as well. Is that how you would do that?
You could say that, but by doing that, you're also somewhat removing the existing redundancy that they have in there, and maybe they want to have some certain redundancy.
Yes, absolutely.
So, I mean, again, I'm trying to like share an idea about the direction you want to go, but there isn't really a silver bullet. There isn't a rule of thumb. There isn't like one thing, one fits all, right? One size fits all. You
No.
gotta look case by case. You know, you cannot assume that I have a 100 horse, I can put 250 horse. You're
Mhm.
definitely gonna have some savings, but is that gonna be sufficient for your customer? And are they gonna be okay with less redundancy? You
Yeah,
know?
I think the answer is it depends. And that's why I cannot get my mind around pumps because I don't know enough. I know a bit and my answers are all, it gets really blurry. You can start with this stuff and you can think you understand a bunch. And then when you start learning more, it gets really blurry. So here is a blurry thing. And I've asked this of other people and I always get kind of the same answer, but it doesn't make any sense, at least mathematically.
Yeah.
You need 50 horsepower. You know, your head and your flow rate requires you need a 50 horsepower pump. Okay.
Right.
But you have a 100 horsepower pump there now, and it's running on a VFD at 50%.
Right.
So according to the fan laws, I don't remember what the number is, but let's pretend, I think it's around 15% or 20% is the energy that's
Yes.
going to be used of that 100 horsepower. So
Yes.
okay, so it's only going to be using 20% of that. So in other words, it's the equivalent of a, so that would be of a 20 horsepower pump. Or I could use the 50 horsepower pump at 100%. Now,
Right.
you would think mathematically, in terms of just math, running the 100 horsepower pump at 20% is going to use less energy than running the 50 horsepower. I'm sorry, running the 100 horsepower at 50% is going to save more, or is going to use less energy than running the 50 horsepower at 100%. But everybody tells me it's the opposite. But the math says it is the first.
It's counterintuitive, right? When we talk about controls and we do our pump sequencing, we load our equipment, right? We load the curves into the system, and then we start running. If you want to run based on efficiency, right? Now you got to run based on the pump curve. You forget about being at 90% and then start the second pump. You forget about that, and it's very counterintuitive because once the curves start going down, you start losing efficiency. That's when you want the other pump to kick in, and very often running two pumps, it's actually makes more sense than running one pump. You know, you cannot answer that without looking at all the possible efficiencies, right?
It depends.
Yeah.
Yes. Yeah. The math doesn't have and it depends in it. It has an answer, and that's what a lot of engineers, they're used to. This is the answer. It's this number, and that it depends, which is more reality based, is hard for some of us, like myself. Okay, so here's another question. I was told that pumps have different curves for each RPM they run at. If this is true, we would need a lot of curves to control for the best efficiency, and optimal control could be challenging with variable flow applications. What is the best way to solve this problem?
Again, you should reach out again to the manufacturer of the pump. Let's say it's a Grundfos, and we should be able to provide you. It's not like you generated different files. Basically, you just have one file, and you're going to be able to see all the curves within what we call the operating range, right? You're going to see the different speeds and how the efficiency goes towards that speed. So it might sound complex at first, but you know, if you look at it, it's very straightforward. You're gonna have your 100% speed all the way down to, let's say, some 30%, and then from there you can see where you want to be within the operating range. So the manufacturer should provide that with one file, one graphic. You should be able to see everything.
Okay, here's another one. Are we also looking at resizing over current protection using existing conductor size?
Very good question. Yes, I mean, every time you come with a new panel, right, new motor size, you want to make sure the electrical components of the building fits whatever you're bringing in, right? It's easier to say, right, oh, is it gonna work? Because you're usually, in most cases, as we're talking here, we're downsizing stuff, right? So yes, like it would fit, but then you're absolutely correct. Like now you're somehow oversized on the electrical component as well. That's very good observation.
let's see, here's one. A chiller's downsized due to a decrease in the building load. The primary pump is sized down as well due to the new smaller chiller. The current issue is the primary flow is always lower than the secondary flow, even though it already runs at full speed. How to address this? Primary flow is less than the secondary flow.
So this person is having what, delta T issues, I'm assuming? You're having more flow in the primary loop than the secondary loop. When you say primary, secondary, that we're talking about the loop system. So again, I need to understand more if you're talking like constant speed primary, variable speed secondary. I don't know what if you have a pumps in your secondary, but if you're not getting flow in your secondary loop, you do gotta make sure you need to first. So it's out of balance, right? So you want to make sure now you're balancing it, and so you get a better delta T. And the flow you want, the idea of balancing is you want to get the necessary flow for all their air handlers, right? As we saw in the little picture here where I show different air handlers, they're gonna have their coils, and then each one they're gonna have a specified number of flow. So you want to make sure you want to have some flow in there. Again, case by case, we gotta look into that. I'd be happy, if you reach out to John and he can connect me, I'd be happy to support on that.
All right. Yeah. If you have more questions on that, just email us at webinars and we'll pass it on to Danilo. Here's a question.
Right.
Can AI help with any of this? I would think AI could help with the whole complexity of all those pumps, the pump curves. The guy was saying, the different pump curves at different RPMs, and I would think AI would be able to do that. Granted, you don't know if it's lying to you or not, but assuming it didn't lie, I think that would be good.
I haven't tried yet. That's a very good point. I will take notes here to try that out. Just feeding AI with the curves and say what will be a good selection here. Yeah.
All right, that was it for my questions. I appreciate your help. I mean, thanks for coming in, Danilo.
Well, I
that was good.
appreciate being here. Thank you very much for having me.
That was a tough gauntlet of questions, I know. It was pretty tough.
You got some good ones. You got
That's a
some
hard
good
part.
ones.
I like the question part the best. I really do. I think that's where I learn the most. Hey, Danilo, thanks so much, and I'll see you all next month. Take care.
See you. Bye-bye.